everyone, and welcome to video number 4 in the three-phase circuits course. In this video, we are going to explore the three-phase loads and specifically star connection. We are going to look for its features and we're going to assess this connection using MATLAB Simulink. So let's start. In this circuit, as we can see here, we have star connected load connected to a three-phase source star connection as well. So we have phase voltages and line voltages. We have phase current equals line current. If you notice here, that one is the line current, but it's the same current going through the impedance. So that one is the phase current. So we can write the voltages as Vn equals V angle delta. Any angle is not necessary to be 0. So Vb is shifted 120 degree from this angle. So V angle delta minus 120 and VCN equals V angle delta plus 120. So let's look for the load now. The load, if the load is inductive, so it will be R plus JXL, for example. So the amplitude of the impedance will be R square plus XL square under the root, and the angle of the load will be tan inverse XL over R. Please don't forget these two brackets. If the load is capacitive, R minus JXC, so Z equals root R square plus XC square, and the angle is tan inverse minus XC over R. Again, don't forget the brackets. So to calculate the current, which is phase current, will be the voltage applied to this impedance, V angle delta over Z angle phi, give you a certain current I angle theta, where theta equals delta minus phi. So we can write current now, IA equals I angle theta, without any calculation because the system is balanced. So IB will be I angle theta minus 120, IC equals I angle theta plus 120. So what is the power factor of the load? Cosine theta V minus theta I, cosine delta minus theta in this case, which is cosine phi impedance angle. Let us take an example. The three-phase Y-connected load shown in the figure is supplied by an ABC sequence, balanced three-phase Y-connected source with a phase voltage of 220 volt, 50 Hz. We need to determine the values of the phase voltages, line voltages, and phase and line currents. We need to calculate the neutral current as well. So, the voltage Vn is 220 angle 25. So VBN will be the same amplitude, angle 25 minus 120. So VCN will be 220 angle 25 plus 120. So that one will be 220 angle minus 95. That one will be 220 angle 145. Definitely all of them are volts. What about the line voltages? So the line voltage VAB, VBC, VCA. So VAB equals the amplitude of the phase voltage multiplied by root 3. And the angle is leading by 30 degrees. So that one will be 25 plus 30. So in this case will be 220 root 3 angle 55. So shifted from this angle 120 minus and plus will give you the VBC. So 220 root 3 angle 55 minus 120, and that one is 220 root 3 55 plus 120. So that one equals 220 root 3 angle minus 65 degrees, 220 root 3 angle 175 degrees. Volt, volt, volt. So we need to calculate the current, so we are going to calculate the impedance. So what is the impedance? Z equals 6 plus J8. So the amplitude of Z will be root 6 square plus 8 square. That one will give you 10. So what's the angle of the impedance? So phi equals tan inverse 8 over 6. Using your calculator, and don't forget the brackets, so phi equals 53.13 degree. So that one is phi. So we can calculate now IA. So IA is VA over Z. So that one will be 220 angle 25 over 10 angle 53.13. So the current is 22 ampere angle 25 minus 53 28.13. So that one will be something like 22 ampere angle minus 28 degrees. So what about IB? So IB equals the same value, 22 angle minus 28 minus 120, and IC will be the same amplitude minus 28 plus 120 ampere. So what about the neutral current? So the neutral current is IA plus IB plus IC. I'll leave that one for you to calculate it and to confirm that the answer is exactly 0. Let us look for the phasor diagram. We have here the phasor diagram of this problem. We have three phase voltages, VAN, VBN, VCN. The amplitude is 220 volt. I plotted this phasor diagram to scale. So we have here something like 5 centimeter represents 220 volt, something like that. So the angle of VN is 25 degrees from the reference, which is 0 angle. So VBN is shifted 120 degree from VA, and VCA is shifted 120 degree from the other side. What about the current? So the current is something like 28.13 degrees, or we can write it 28.2 degree from the reference, and B current or phase B current is shifted 120 degree from phase A current, and IC is shifted another 120 degrees. The same amplitude, which is 22 ampere, because the system is balanced. What about the line voltages? So the line voltage is 220 root 3, but shifted 30 degree from the phase voltage, as you can see here, but from the reference here will be 25 plus 30, so that one will be 55 degrees. So definitely phase B is 120 degree from this green line, so, and that one is 120 degree from this one. So that one is 120 and that one is 100. I cleaned the phasor diagram to show you how to find the load power factor. So if you notice here that the voltage VAN is 220 volt with angle 25, so that one is theta V. And the current is lagging by 28.13 or 28.2, so that one is theta I. So theta V minus theta I will be 25 minus 28.2, so that one gives you angle between V and I 53.2. So the power factor is cosine 53.2, which is the impedance angle, and we can say that one is lagging power factor because the current is lagging the voltage. Don't forget that the reference is 0 angle, so we measure everything regarding this reference. So that one is 25, that one is 28.2, so the power factor is 53.2. So now it's time to confirm these results using MATLAB Simulink. We are going to simulate this circuit using MATLAB Simulink. So the phase voltage is 220 volt angle 25 degrees. The load is balanced. The impedance is 6 plus J8 ohm per phase. So we are going to build this circuit using MATLAB Simulink. I'm going to speak about this circuit in details when we are going to move to the Simulink platform. So these are the results. It's not clear at all. We didn't see anything. So this is why I magnified this one for you. We have phase or line current because that one is a star connection. So the phase current is a line current in the star connection. We have phase voltage, we have line voltage. So the results are arranged as phase A, phase B, phase C, and that one is the magnitude and that one is the angle ABC. And for voltage as well, phase A, B, C, and that one is the angle for ABC. And that one is VAB, VBC, VCA, and these are the angles. Right, so if you look for the current is 22 ampere for phase A with angle minus 28.2. And for phase B and C, they are shifted minus 120 from this angle and plus 120 from this angle. Regarding phase voltage, 220 volt, 25 degrees for phase A, so shifted minus 120 and plus 120. For line voltage is root 3 V phase, and that one is RMS value, so root 3 multiplied by 220 gives you something like 381. You can check using your calculator. So that one is 381 volt, and the angle should be leading this angle by 30 degrees. So 25 plus 30 give you something like 55. So from this 55 minus 120 and plus 120. These are values. What about the waveforms? Let's look. We have here three figures, so let's start by the first one we have here. In the right side, I'm going to measure the current. In the left side, I'm going to measure the voltage, and the x-axis is in degrees. So I'm not going to put the x-axis in time, but I put it in degrees. So if you look here, we have the blue waveform is the voltage, the red waveform or the orange waveform is the current. So you can measure the magnitude of the current here and the magnitude of the voltage there in the left side. So you're going to the left side, you measure voltage, right side, you measure the current. But that one is not correct because we feel that the current should be 22 ampere and the current here is something like 30 something. So 22 is RMS value. Don't forget these are RMS. The voltage here is RMS, but these values are peak. So that one is a peak value. Let's look for the angles. That one is a zero angle here. So the current is lagging by 28.13 and the angle between the voltage and current is 53.13, which is the impedance angle and the power factor angle. So cosine 53.13 give you the power factor, theta V minus theta I. Let's look for this figure. We have here the three voltages VAN, VBN, VCN or VA, VB, VC, and the value here is 311, which is 220 multiplied by root 2, peak value. Check using your calculator. 220 multiplied by root 2 gives you 311. And the voltage, if I start the 0 degree here, is leading by 25 degrees, as you can see here. Regarding the line voltages, VAB, VBC, VCA, they are shifted 120 degrees as well, but the value here, peak value, is 538.9. So 538.9, if you divide it by root 2, will give you something like 381. You can check using your calculator as well. Let's look for the angles here. If that one is a 0 point, so we notice that VAB should be shifted from the 0 point by 55 degrees. Look here. And from phase A, that one is a dashed line, is phase A with peak value 311. That one is shifted from 0 by 25 and that one is 30 degrees. So line voltage leads phase voltage by 30 degrees. And phase voltage is leading this 0 point by 25. So this angle for the line value is 55 degrees. So we need to know how to build this system, how to find these figures. We're going to move to the Simulink platform now. Before moving to the Simulink platform to check the star load, let me remind you, for model setup, please refer to Induction Machine Course Chapter 5, video number 2, Dynamic Simulation using Simulink. So I'm not going to explain the setup again. I'm going to look for this circuit, how to build this circuit, and how to get the results from this circuit. Let's go. As you can see here, this is a circuit we want to simulate. We have a star connected load with 6 plus J8 ohm impedance per phase, and the voltage applied, phase A voltage is 220, angle 25 degrees. So I explained before in video number 1 in this course how to add an image. So that one is video number 1, which is that why three-phase outperforms single phase. So refer back to this video to see how to add an image to your model. So here, if you notice, I added 3 single-phase sources to make a 3-phase source. So if you click on that one, I'm going to add that one, 220 volt root 2, because this source asking for peak. And the phase in degrees will be 25, frequency is 50 Hertz. So definitely for phase B, you are going to have 220 volt root 2, the same, but shifted minus 120 plus 25, and that one is definitely 120 plus 25. Can we have a 3-phase source directly? Yes, if you go to the library and check here for electrical specialized power system, going for sources, electrical sources, you are going to find a 3-phase source. If you drag that one and drop it here, so don't forget that one has an impedance. So if you click on that one, you are going to choose that one is a star or star grounded. You are going to adjust the frequency. You are going to adjust the voltage line value, not phase value, RMS. And then you are going to put the impedance for the source. If you don't have impedance for the source, you are going to put these as zeros, and then you are going to have a direct source. But that one is all the time either star grounded or star with neutral. So we can build the source using this one or using this one. Also for the loads, you can have a load or a branch, or you can have a three-phase load. So you can drag one and drop that one from the library here. So I'm connecting the supply here, phase A, through an ammeter, and that one is connected to the phase A load. And then B, then C, and then I have a neutral point here. So that one is a neutral point, as you can see. And then I'm going to measure the voltages, phase and line. So that one is phase A voltage, and that one is connected to the neutral point. So that one is going to measure the neutral point here. So that one is a neutral, A, B, C. So these voltmeters are going to measure phase values. But these ones are going to measure line values. We can see that one on the scope here. We can measure the results as a values here. Regarding the currents, I'm going to measure these three currents. I'm going to add them together because these are the neutral current. I need to check that one to be 0. So let's run that one. So we got the results here. The current is 22 ampere RMS value because I adjusted this block before. I showed that one to you before in video number 1 again. So here you are going to measure magnitude and angle. I divide that one by √2 to have the RMS value. So that one gives you phase A, phase B, phase C magnitude, and these are the angles. And that one matches what we have in the previous slide. The voltages, phase voltages are 220 volt, and these are the angles, 25 and shifted, 120 positive and minus, and that one is something like 380 volt or 81 volt, and these are 55 degrees for the line voltage, which is leading the phase voltage by 30 degrees. Let's look here for this scope. So this scope is going to show you that one is phase voltage and line voltage. So let me show that one to you again. So that one is going to measure the phase voltage, and that one is the line voltage. So as you can see here, that one is a phase voltage and that one is a line voltage. So the line voltage is leading the phase voltage by 30 degrees. We didn't notice that one. How do you know that one is a 30 degree? I'm going to show you that one now when we're going to the MATLAB Workspace. Right. So let's look for the value of the neutral current now. So the neutral current is 1.7810 to the power minus 11, which is exactly 0. If we look for the currents here, we're going to find these currents, something like 31 ampere. I told you that one is a peak value. If you divide that one by √2, you can get 22, and they are shifted 120 degrees. So these are the currents. And if you look for the phase voltages, so that one should be something like 311, and they are shifted 120 degrees. And again, for that one, something like 540 volt, and that one is line values. So let's go to the MATLAB Workspace to see how we are going to plot something like that one to detect the angles. So if I like to take the waveforms to the MATLAB Workspace, I'm going to click on the scope here, click on this gear, logging, choose any name you like. I choose here VMV because that one is phase voltage and line voltage. And then for the format, you are going to choose from them array. Apply. Okay. But I notice here that the waveform is not smooth enough. So I'm going to change that one in the modeling. So modeling, model settings. Then I'm going to change the maximum step size. Instead of 1 to the power minus 3, I'm going to make it 1 to the power minus 4. Apply. Okay. So let's run. Simulation. Run. So I presume that one is change it now. That one is pure 22 ampere exactly, 220 volt exactly, as you can see here. So let's look here for the waveforms. They looks more smooth. So I'm going to the MATLAB Workspace here. So let us plot this waveform. I'm going to write plot VMV all in 1, VMV of all in 2. So 1 is time, 2 is the phase voltage. So we are going to have here the waveform, which is a phase voltage, and these are the y-axis and x-axis function of time. So I'm going to hold this figure, I'm going to plot in the same figure VMV and 3. 3 represent the line voltage. So if you look here, we have phase voltage and line voltage, they are in the same figure. But that one is not clear to us as well. That one is function of time. We need to make the x-axis function of degrees. So what we are going to do, I'm going to close this figure. I'm going to plot that one, but I'm going to plot that one now. Make that one phase voltage, so I choose the column number 2. But here, you know that the supply is 50 Hertz, so the periodic time is 0.02 second. 1 over 50 is 0.02. So how to convert the 0.02 to degrees? We know that 0.02 represents 360 degrees. So if we multiply by 360 over 0.02, that one gives you degrees. So we are going to check what will be the figure now. So we have here in degrees, hold, plot for the line voltage, make that one 3. So we have the phase voltage and line voltage function of degrees. But that one from 0 up to 1200, because we have 3 cycles, we can make that one cycle. I'm going to click on this arrow and then click here. So I'm going to bring that one to the right side if I like. So then I'm going to change that one. Rather than going for the text, going to the ruler, I'm going to make that one here from 0 up to 360. And then that one gives you 1 cycle. And then, so that one from 360, we're going to have the text from here. So we can change the text. I'm going to change that one to you. I'm going to change the text in terms or steps of 30 degrees. So I'm going to remove all of those. And then I'm going to add 30 degrees. Let me add the grid. So if you check here between this point and this point, so that one is roughly 30 degrees. Can click here. So I'm going to remove this arrow. So that one. So this point is something like 125.3. That one is the x-axis. And that one is something like, let me going for this one. So that one is 154.8. So the shift between this one and this one is something like 30 degrees. So that one is a line voltage leads the phase voltage by 30 degrees. And you can apply that one for the currents, for the phase voltage, for the line voltage. So if you like to return back here, you can do the same for line voltage or phase voltage or the currents. I'm going to return back to our slides now. Now we can summarize the star connected load. In the star connected load, we have phase voltages, line voltages, phase or line currents. They are the same in the star connection. In phase voltages, we have the voltage V for all the phases, and they are shifted 120 degrees for phase B, minus 120 for phase C, plus 120. Regarding line voltages, they have the amplitude √3V of the phase voltage, and they are leading the phase voltage by 30 degrees. For the current, it depends on the load, inductive or capacitive, but they are in phase or lagging or leading these voltage. And phases B and C are shifted from phase A by 120 degrees. So we can summarize that one as the line voltage leads the phase voltage by 30 degrees. The line voltage equals √3 the phase voltage. The line current equals the phase current. The angle between phase voltage and phase current is the load impedance angle, and that one is a power factor angle. For balanced load, the circuit can be solved per phase, and other phases are shifted by 120 degrees. What will I watch in video number 5? In video number 5, we are going to explore delta load analytically using MATLAB Simulink. See you in the next video.